Good afternoon, respected dignitaries, estimated participant, and dear colleagues. It is my great pleasure to welcome you to the technical session 30. This is the last session of this AICTE sponsored ATAL Faculty Development Program. As we continue to explore into transformative technologies and methodologies, today's session holds a huge value for anyone strong on research and innovative into the field of additive manufacturing. The topic for this session is programming skills required to carry out research in additive manufacturing. Focuses on the critical programming competencies essential for optimization and advancing additive manufacturing techniques. We are extremely privileged to have with us Dr. Prashant Kumar Jain sir, professor from Pandit Dwarka Prasad Mishra, Indian Institute of Information Technology, Design and Manufacturing, Jabalpur. We are extremely privileged to have with us, sir, a highly accomplished academician and researcher in the field of manufacturing technology. Dr. Jain, sir, is currently a professor in the Department of Mechanical Engineering at IIITDM, Jabalpur. With over 25 years of teaching and research experience, he is a leading expert in additive manufacturing, computational modeling, CAD/CAM integration, and rapid prototyping technologies. He completed his PhD from IIT Delhi, focusing on part strength studies in selective laser sintering process, a key area in additive manufacturing. Dr. Jain has an extensive portfolio of more than 195 publications, guiding numerous PhD and master scholars. And he is also spearheading impactful research projects in his domain. His vast knowledge in programming tools and their integration with manufacturing technology makes him uniquely positioned to guide us through this section. In today's session, Dr. Jain will explore core programming skills that are vital for research in additive manufacturing. The application of tools like MATLAB, Python, and other software in optimizing additive manufacturing processes that we learn with the help of Dr. Prashant Kumar Jain sir. The insight into how computational model can enhance the accuracy, efficiency, and quality of 3D printing component that will be explored by the Jain sir. Next one, practical example showcasing the integration of programming with manufacturing process that is also covered into this session. This session will provide a comprehensive understanding of how programming acts as the backbone of research and innovation in additive manufacturing. I now invite Dr. Prashant Kumar Jain sir to take the stage and share his valuable knowledge and expertise with us. Sir, over to you.
Thank you very much to the organizing team, Dr. Abhay, Dr. Santosh Jaju, and the entire team for this FDP and giving me this wonderful opportunity to interact co-researchers, and that will give us opportunity to have the learn from our peers in the domain. So it's a two-way communication. In this session, since it is the last session, the few initial slides I will take on 3D printing, and I would like to know quickly if you are already gone through those things, just raise hand and say yes, so that we can come across. I have many things to share with you on the programming part, MATLAB programming, Python programming, and how these, as already told to you, how these things will help us to take the research forward, and why the programming is necessary for us if we really want to be innovative and to carry forward the research. Otherwise, many softwares from open-ended to lakhs of rupees softwares are already available. You can also explore the things which you can do in the mimics, very much included in the title of the course, mimics and its counter colleague software like Magix. So what the things you can do, magics and mimics, can you do these things by your own also? This session is mainly dedicated for that. All may be not lucky like GHRCE, so have the software mimics and magics. So even then also, can you do your minimum work to carry forward the thesis, your research work? You should not hinder because of the software availability. So let me open and share my screen. Okay, I think I should share this screen, Hindi news. So my PPT will go. Okay, I'm using two monitors right now. So if there is not visible my screen, just let me know. So I will switch over from one screen to another screen. Yeah, I hope you can see one of the screen showing the news,
Yes.
right? I hope now it is in the PPT mode, right?
Uh, no, still that news is only visible.
News, okay. So that means it is taking a tear actually. Let me share again. Okay, can you see the
Yeah,
PPT now?
yeah.
Okay, fine,
Now it's
fine, fine.
okay.
So if I will run some video in between or some other software, if there is an issue, you just let me know. So I will switch over my screen from one monitor to another. Okay. So in this session, we are going to study or talk about the programming skills required to carry out research in the additive manufacturing. Few things I would like to take first about the additive manufacturing. We start generally for making any product. Suppose this kind of product is there. So quickly, by looking at this picture, we will to understand that this may require the machining. So immediately the first impression, we got the machining. Then we thought that, okay, this product can also be made in the joining process, soldering, welding. But the most popular and common one is the forming processes like injection molding, right? But now we are in the era of additive manufacturing, which initially started with the layer deposition. RV called the rapid prototyping. Then the most widely acceptable technical name has come, that the additive manufacturing. Then it is also nowadays known as 3D printing. Mostly don't require any engineering background. Food printing, tissue engineering, many things. So not necessarily an engineer, but the 3D printing is known for everyone. Right. So why this we go for additive manufacturing? That process allow us to quickly build a 3D model. Right. This already you have gone through, and you see here one example I have shown. This is a handpiece of a hair dryer gun. Right. You see otherwise how much drawing sheets, dimensions are required to be transferred to develop this injection molding die to create this part. So initially, when even I started my PhD in 2005, at that time, this was just a communication tool to communicate your geometric model. So often what we call is that the pictures can communicate, right? So we started communicating to the patent office while creating a geometric model, physical model, to communicate it to the patent office. Okay, this is the product, we are going to have a patent. So in case of this additive, the counter thing is the subtractive machining, right? So what is there in subtractive? We are removing the material. Okay, so in case of subtractive process, we can begin with a solid stock and we need to carefully remove the material, right? But the process may be sometimes very complex, exhaustive, maybe time consuming, and maybe material is very costly, so we may not be able to even build the part, right? See, for example, this case. In this case, you can notice here in such areas the CNC machining is not possible. Here in this case, the CNC machining is not possible. Your 5-axis CNC machine tool cannot even reach to this area, right? So this is the removal process and this is the additive process. So generally, we in such cases, we prefer to go for additive processes. And I believe that during the previous lectures, you have already gone through that, the different kind of additive manufacturing processes. Somebody can answer these questions in the chat box, keep on writing. So I'm coming back to additive manufacturing, that the complexity of the part is no more a limitation. Means whatever you can think, whatever you can design, and imagination, you can print the part directly. So why I said it is started with the communication. Generally, if you go a carpenter shop, you don't want to tell him. Either he will show you a catalog to decide the furniture which you want, either you will start using a pen and paper and draw something, right? So a picture is worth 1,000 words, often we say. But when we come into the era of 3D printing, rapid prototyping, or additive manufacturing, layered manufacturing, we come across the model, and the model is worth 1,000 pictures. So instead of pictures, now we are communicating with the model. So you see some of the examples over here, like this geometric model and the physical model of the heart. You can see the different colors here, and these are the veins are printed, right? Some functional springs, some engine blocks, toys, and this temple model, right? You know, because this product development cycle has become so fast, you do not find any shoe design or tie design again and again in the market, right? Every time what happens, you go into the market, you will find a new design, because developing a new product, launching it to the market is become so fast. Nobody would like to use the previous designs, and no consumer would like to have the previous product, right? So this is why we go for the additive manufacturing. It can be a mechanical product, it can be a medical product as well, right? And we call here the layer deposition, right? So you remember, you have the X-ray already, right? The Dr. Khalatkar was telling me about the session already conducted by the dentist, right? So I will come across to that also towards the end of this session. So here, the thing is that everything is done in a layered way. Everything is done in the layered. You want, what is layer? You want a cross section of an object. Like here, you can see these layers. So the stair-stepping effects you can see, right? You can see here this layers. You can see, find out on this object. You can see this layer, right? So we will start with the basic, where you can understand where is the scope for programming is required, why it is required, right? So look at here, the initially you want this CAD model, right? So this model, Dr. Khalatkar, our participants are allowed to write the comments. I would like to know who is using the AutoCAD or Pro, or which geometric model you are using. Yeah, one is Fusion 360. Yeah, please keep good. Muthu Kumar, please, others can write whatever you are using, CATIA, Pro E, SolidWorks, very nice. So here you see this CAD model is required to be created in any of the solid modeling packages. That may be the SolidWorks, Vision 360, AutoCAD, ZWCAD, Solid Edge, or CATIA. Okay. Now the second step comes is here is the slicing of the model, right? So slicing means what? You need to cut this model, right? And this model cannot be cut by a knife, because it's a virtual model. It is in a computer. It is a mathematical model available in your computer system, right? So this computational model can be cut down by the computations only, right? You require a, right, yes. So you can use many FlashForge, Cura softwares for slicing, right? This session is especially what Cura or your FlashForge or Magix is doing for slicing, right? And how we can do by our own this slicing. So you see, remember, notice here, these are the tapered edges coming, right? These tapered edges, because this model is have the sculptured surface here, so we need to square them, right? Now you see here all the layers are now in a cuboid form, prismatic form, right? Once we got these kind of prismatic form, layers means this contour information. So suppose means I will select this area or this area, you want this kind of contour information, right? This contour information is required to be stored in your computer system, right? That is the objective you have to fill. Means this is one contour at this side, here is the different contour, here is the different contour, and then successive layers. The moment we keep on in Z direction, upward direction, this movement will be, and this contour will be changing, right? Our objective to find out this contour, okay? Then we will move to the nozzle path. I am coming to the process, right? So next step, once you get this prismatic information, you need to join them. Packing is required, right? We call it the staking or packing, okay? Then you have the physical prototype, and this physical prototype will be in this form, right? What happens? You started with this CAD model, very smooth, but you are landed up with this staircase model, right? So what is happening? These stairs are inherent characteristics of the process because everything you have done with the layer. So any layer will be in a prismatic form here, cuboid form. So there will be a stairs generated here, okay? Now see, because your desired model was this, but you are receiving this, so you have to move with the post processing, right? So a lot of grinding, surface finish, polishing, or some other things like we use the selective melting. Dr. Taufik might have discussed with you the selective melting processes to get this model, right? So our objective is to get this finished physical prototype after the post processing, okay? So let me come to the process here. What we have done, we have created the geometric model. Then we have done the tessellation. Any idea of the tessellation? Quickly you can write in the comment box. Any idea of the tessellation? What is the tessellation? Okay, STL file, okay. Okay, anybody else? Tiling, okay, anybody else? Sudhir, tiling, okay. Triangles, okay. Okay, so basically the triangles or STL file is the output, you can say, or the presentable form of the tessellation, right? So tessellation basically tells you the piecewise approximation of the surfaces. Means whatever, suppose this is the cube you have, right? And we piecewise approximated, right? So the piecewise approximation of the surface. This surface can be anything. This can be triangle, this can be square, pentagon, hexagon, or anything. But finally we landed out with the triangle like this. Why? Because the triangle is the simplest geometry or the lowest side plane, right? To create a plane, what we require a three, right? We can also have this, right? This can also represent, but for the minimum plane is the triangle, to cover the maximum volume is the, right? So that's why we piecewise approximation is done. This can be done by using any polygon, but we prefer to use the triangle. That is known as the tessellation, right? Which the called as the STL file. With the very initial stages, we have used the STL file. Like nowadays, many other formats are also available. Okay. So what is happening in the tessellation? The piecewise approximation of the surface. You can see this cylinder and you can see this another cylinder, right? You see here this cylinder. What is happening here? You have the smooth cylinder, curved surfaces, but here what happens? Just like you can imagine, you have a knife in your hand and you are peeling it off a potato or an apple, whatever you would like, and you are converting the spherical surfaces into a planar sections. So there are planar sections and every section is represented by a triangle. In this case, you can see this surface can be represented by a rectangle also. No issues, right? But still we are using the triangle because the file format says the triangle. I will show you at the end towards the session. We are working on developing newest format which do not necessarily require the triangles. We can use any shape of the geometric model. Okay, so that we will take up, or else okay, I can also take it right now. So that is the tessellation, right? Then we need to do the slicing, right? Actually, our ultimate objective is to get the slicing. So this tessellation is basically providing how to do the slicing. This is just a facilitation for the slicing to be done, right? So here you see, if you take this plane cross section like this, right? Here the equation will be very difficult because you have to deal with the equation of a cylinder, or it can be anything. You can have a mouse product, or you can have any typical product, and once it is in the surfaces form, this can have the many things to do. An equation may be complex, but once you reached into this position, STL file or the tessellation done, here you can see the equation is reduces to a equation of a plane and equation of another plane. This another plane itself is in a form of a triangle. Okay, this part, how to proceed for tessellation, I will take up little later. The next step after slicing, this slicing you achieve with the tessellation, right? So you remember here, tessellation is not a necessary part of the process chain. Tessellation we are doing just to facilitate ourselves or make easiness for the slicing procedure. Okay, then after slicing, we do the generate laser scanning path, this laser scanning path like this. Okay. Then we have to print the part on the RP system, right? And then just we do some post processing to get the final product, right? And then we check for dimensions, for accuracy, and surface finish, our orientation, many things we can carry out. Okay. So this is the way we proceed with the process chain, whatever we call the rapid prototyping, AM, additive manufacturing, or 3D printing. Okay. Now see how this is going to be implemented. That is the main part. So you see this part, I have geometric modeling done in Pro E. Okay. Now you can see within this part also, see I have taken some kind of surface. This geometry inside, this is the hollow portion. Inside this is also a hollow portion and different. Right. Now we will convert this into the STL. See, this is the conversion of STL file. Did you notice it? All our triangles are here in this file, right? You see here all the triangles, and in this triangles also you notice here the planar section, so only two triangles. On this top surface you will notice there are two triangles, right? Because they are sufficient to represent the surface. But you see in the cylindrical part, what is happening? So many triangles are there. Here also so many triangles, right? Because every surface is to be converted into the planar section. The requirement is not the triangle, but the requirement is only the planar section. And that planar section we are representing with the so you see here, if we increase the number of triangles, what is going to happen? We are more close to the required geometry, right? If less number of triangles are there, the lot of volumetric loss will be there, and we may lose the original designer intent, right? That is the issue with that. Okay. Now we go for this plane. Can you notice here in this plane what we have done? Here you can see the blue color dots. Can anybody say what these blue color dots are showing in this picture? Can you see the zoomed portion of my screen? Fine, Dr. Sahu. Yeah. Support structure needed, okay. Anybody else? You see here at this height, 8 millimeter jet mm, this green color plane is showing. This is the horizontal plane. Just like in vertical direction, we are moving, right? And here this STL file in the green color, the previous scan, here only the triangles with the red color are shown. Okay. And these blue color dots are showing the intersection point with the plane. Got it? your response is needed, right? The blue color dots are showing the intersection points. Yeah, thank you, Dr. Sridevi. Okay, so you see these are the points, intersection points we got from the STL file, right? Now what we will do, we will plot these points. You see here, the result is this. Because all these STL files, all these triangles are a random way. They are not in some sequence. Okay, I will show you one STL file little later. Anybody have opened the STL file in Notepad? Say yes or no. I repeat my question. STL file opened in Notepad or WordPad? Say Muthukumar one yes. Okay. Anybody else? Yes. Very nice. Have you developed any kind of Nilesh? Yeah, Notepad. Okay, very nice. Have you developed any kind of MATLAB program or Python program to read that STL file? Reading that STL file in MATLAB or Python? No. Okay. So you see here, the next task is to connect all these points in a logical sequence. So this information can be used for further processing, right? Right now it is not in a useful way. So now you see here, can you notice here? See, in this case, the blue color is showing the external contour, the red color dotted line is showing the internal contour, again the external contour, again internal contour. These are only external contours, right? And you can relate it also with this figure. If I cut this point at 8 mm height, right? So what you will receive? This portion. External contour, internal contour. Like this. Right? This information is required for us that can be used for our 3D printing machine. Okay. So here you see the next step is to generate the nozzle path, right? Whatever we have seen here. So what is nozzle path means what? This portion you want to be solidified, right? Okay. Here no solidification. Here again you want the solidification, right? Similarly here you want the solidification. Here you want the solidification, right? You can relate with this object. Okay. So yeah, we will reach to the G code. How to generate? Dr. Muthu Kumar, how you have generated the G code? By your own or by through the Cura or FlashForge or Magix? Okay, you generated through the Cura. Okay, very nice. We will discuss how you can get your G code by using the MATLAB. Yeah, KISS slicer is also very good. Yes. So see, this part has to be solidified. Once you take this geometric model, you can take it to KISS slicer, Cura or FlashForge or anything else and you can get the G code. Very nice, right? Now point is here, after that G code, if you want some more modifications, say for example, if you are good in doing 3D printing, I would request you, if you are allowed to unmute, you can discuss your ongoing research problems, what you are doing. So where this programming information can be helpful for you. Okay, next 15-20 minutes I will take you to the programming, then you can open up for open discussion. Okay, so see here, this information has to be converted into the this kind of nozzle path. Now look at this, what is happening with this nozzle path. Like this. This is the pink color area. This required the solidification and remaining here. Can you see what the logic can be fit here to the G code, where the nozzle has to be switched on or switch off, means material will be deposited or material will not be extruded. Or if it is a laser processes, I hope you've gone through the FDM and selective laser sintering processes, right? All of the processes you have gone through. Say yes or no, okay? So I will not jump into the FFF process or SLS process, where the lasers are used to solidification of the part. Okay, so you know FDM, you know SLS process. Okay, now see here what we can take up here. Suppose I draw a line, say for example here. So it is here the first intersection. I can inform to the machine that the laser has to be switched on. at the second intersection, I can tell to the machine that the laser has to be switched off, right? Similarly, the next intersection point, I can again say switch on, switch off, right? On, off, on, off. And you see here, in this way, you will find that the on, off, on, off, on, off, on, off. And in this way, you can tell to your machine, and this logic you can convert into a G code information, that where the laser has to be switched on and where the laser has to be switched off, and the laser will go up to this point and then come back. Again, follow the same thing, right? So we can think in a logical way. I hope, can you tell everybody how many of you are gone through the MATLAB? First, my basic question, the programming anything. So you have done some work with the do loop, for loop, if loop, switch statement, these kind of basic things. So where you, yeah, one yes, at least 5 responses, yes or no, anything. So that can be, I will take up the discussion up to that level. Yeah, Dr. Anil Sahu, Dr. Gururaj Bowler, 3 responses. Okay, so in this way, we are going to convert into the program, right? Now, okay, Priya Ranjan, no, 4 responses. I'm waiting for one more row. In the meantime, I have you gone through this magic software? Okay, magic's no. Let me take you briefly directly on the software itself. Okay, I am just taking you to the software screen. Can you see now the software screen? I'm moving from this monitor, one monitor to another. Yeah, thank you, Dr. Rupesh. Yeah, okay. Now you can see on the screen the magic software, right? Sorry. So, like other software, we have the many tools, right? This is just the materialized software, right? You remember you are using on the Mimics software. The Mimics and Magics both are from the materialized software. We have the license for both Magics and Mimics available in our laboratory at IIITDM Jabalpur. Now look at this part. 3 spheres inside, right? I will show you one video of SLS process so you can relate it, right? And there is no joint, right? This kind of applications we require for any biomedical applications as well, right? So look at here. Now what is there? Let me put it in a triangular way. Can you see everything is now converted into the form of triangle? Just wait. I think I have undone. Right? Look at this. Everything is in the form of triangle. Let me give you a zoom picture. Now see, everything is in the triangle, but depending on where are the triangles are required, some less triangle or how more triangle. Like you can see in this vertical one, how small triangles are there, right? Here are the triangles, right? Our next, you remember what has happened? The software has done the tessellation for you, okay? Our objective is to get the contour information. Let me put you. Right, this is the STL file look like this in the software. Any STL viewer you can use for this purpose. Okay, now let me convert this into the, so you can see it. Now look at this. If I go to show you the section, can you notice here, this is the sectional view you can see here, right? This red color, can you see here? This red color means in this portion, this much material has to be solidified, right? If we want to this much material to be solidified, what exactly we need to supply to our machine? And you talked about the G code. What G code is required at this level, right? You require these 4 blue color contours. 4 separate contours are there. Or let me put it at the more bottom side, okay? See at the initial contour. Initial contour will be this kind of circle that need to be solidified. So you are generating a nozzle path to fill this circle, right? And this information will go to your 3D printing machine in a form of G code, right? The same G code we use to run the CNC machine. Okay. Only difference is that for CNC machine, our approach is from top to down, and here bottom to up, because we are depositing the material from bottom to up. Now look at this, the moment I move it vertical direction. See here, the cross section it changes. At this stage only that the spring part, this much portion is solidified, remaining is unsolidified. See here like this. Here at this first sphere and the second sphere, both are printing together, and there is a clear cut gap between first sphere and second sphere. Anybody, how this will be supported in this case? You gone through the SLS process? Anybody can answer quickly this? How the second sphere will be in its position, and it is printed and it is separate from the first sphere. Powder, okay. You can say unsintered powder will be remain in its position. So that unsintered powder will provide the support to the second phase. Very nice. Thank you, Dr. Sudeep. Okay. So see the movement we will come upward. Right, the first sphere, second, now the third sphere will start building, the fourth sphere, fifth sphere, like this. Got it? Up to the final. Right? Remember, if we are here in this portion. Okay. Now look at this. If I go and into show you the triangles, right? And you see over here these triangles. These triangles are now the part of the intersection point we have to collect. From those intersection point, we have to join them in a logical sequence to convert them into the triangular contour information, right? That will give you the contour information. Okay, so this is the way how your magic software or any other software works to get the contour. Remember here, what is required? We want a contour information. Anybody, how we generate the contour information, how we supply the contour information, right? Have you heard about the CLI file? Common layer interface file, anybody? I hope now you can see my PPT on the screen. Anybody? Any idea of the CLI file? So you see this screen, the cut cross-sectional views I have shown you, and you need to know the lot of manipulation with the STL file, right? This I have shown you. Okay. Then we are coming to the STL read. I will show you it in the again in the MATLAB, right? So anyone have any idea how the contour information or contour layer information or SLI file slice layer information is supplied to the machine, 3D printing machine, like the I'm talking about, not this our very simple flash forge kind of printer, but for say US optical machines, right, are the big machines which use on the powder based, right? Okay, let me show you one powder base also. Can you see this screen? Can you hear the sound as well? No. Okay, sound is not transferring. Well, okay, I will explain. Let me mute also so I can talk. But I hope this SLS process video you have gone through, right? This is a selective laser sintering process, and you can see powder is sintered by the laser. So inside there is infrared heaters which do the preheating process, and remaining 4 5 degrees centigrade temperature rise occurs because of the laser. Okay. So you can see here the laser reflection is coming because we have done this experiment with the mixing of nano clay. So because of nano clay, this is reflective. Otherwise, it's a simple polymer polyamide 2200. Right. So we gone through this. I assume that SLS process is very well known to you. Powder support is not required, and now this has reached to the metal 3D printing. Right. So here, suppose the powder is 150 micron, and here is the 20 micron steel powder is there. Again, the neck forming tendency is there. Right. So you see here. Otherwise, these kind of complex part is not possible. Okay. So let us come back to the STL file reading. See this STL file, how we are reading this STL file in the MATLAB. Okay, let me run the MATLAB also. I hope now you can see the MATLAB screen. Okay. MATLAB screen is visible, right? So let me run that file first. The CLI file read little later we will come. See this file. Okay, and you know like if you have done the simple even C++ programming, you can quickly understand this is a very basic programming. A text file is opened, right, over here. A text file is opened just, and this text file is read in a MATLAB programming, and different characters is identified and converted into a mathematical information, whatever contained in the file. So let me run this file, STL reader. Okay, this is just like professional software. It is a own written program, right? Not a commercial software. So you see, I'm just opening, since we are talking on cube, so let me open a cube only, right? You see over here, let me put the output. It is going to the next slide, right? You see this cube we have read into the MATLAB. Okay, now you see all. How many triangles are there? Anybody can write? Total faces are 6 in a cube, and the total triangles in a cube are, yeah, thank you, Professor Solanki. Right. So because what happens, every faces is now converted into the triangle. Okay. So 12 triangles are there, total 8 vertices, but now this STL file will have 36 vertices because the 12 triangles, every triangle will have 3. Now see what happened in the command prompt. See, for every triangle from here, this whatever the variable I have given, -100. Can you recall what it is showing? The first row, normal to the facet, and the next line is x1, y1, z1 for the first, okay, the second and the third, right? Very nice, right? So all the 12 triangles information in a mathematical form is now available with us. The next step is to get the triangles, get the intersection of this file, right? Let me take you, then I will go back to the PPT little later. Okay, so this is one. Now remember, if I open this file, this is the cube I have taken. Now let me take say this file. Okay, okay, this is what Let me open another file. Okay, let me go back to some other file. Dropbox. Okay, let me open this file. Okay. You see it is giving some error. Can you notice why this error is coming? Can you read this error message? This file is not able to read this STL file, showing some error at line number 25, right? But let me run another MATLAB program, this MATLAB program. Let me open the same file. Okay, I have gone through this, data preparation, right? Let me open this file. See, this file is read, working fine. Can anybody tell me what may be the reason? I'm using two different MATLAB programs to read those two STL files. The same data is again recovered. 555. I will talk. The reason is, anybody wants to type something? You type, or else I will continue. Okay. So the reason is here, you see here, two different things. You see, on the left side, I have shown you the file which is generated by the SolidWorks or AutoCAD, and in the right side the file is from the Magic software, right? The Magics I have shown you already, right? So you see here what happens, the writing the file index is like this in a tab format, right? The facet normal, the vertex is there, right? Here the facet normal. So every paragraph what it is showing, the solid cube STL, the facet normal. Then the outer loop, 1 2 3 3 vertices, end loop, and facet, finish, one facet. See what happens here, it is doing facet normal, right? It is in completely decimal format, right? Here it is in a scientific format, so every information is written in a scientific format, E format, exponential format, and here this no format. Everything is starting from the first character. So if you remember, if you see what is happening, this is going to be because of in this MATLAB. You see here, this program is going to read all the text, right? So that's why we need to change, or we need to identify this file is exported from which software. This otherwise you may not be able to read. So your program is specific to the file, STL file structure, right? So you remember this file, just we have used your file name, path name, UI get. So this will open the STL file, right? This is file open, ID open, right? Then we will just open this file, and here just it is plotting the file. Okay. Similarly here in the also. Only thing here we have made some changes so that it can consider that the index part or the tab form, right? This is how we generate, right? Now let me take you how we go for the slicing first, then we will move to the back to the PPT. Or before that, I will let you first, let me run. Okay. Yeah, I have. Now see this bigger program, right? We have read the STL file. We have generated the mathematical information for each and every triangle. Our next task is to get the intersection of that triangle with the plane, right? Plane is parallel to XY plane, which is moving successively in the Z direction, right? Now look at this here. Let me run this file. And let me take again STL file. Since we are talking on cube, so let me take a cube only. Okay. See here, this is the cube, and it is asking, because now this is my program, it is already knowing the geometry minimum is Z, and the geometry in Z direction maximum is 50. So let me put some value, say 34. See here, this is going to be the STL file. This is going to be the contour information, and this is going to be the contour connected in a logical way, right? I hope you can see all three figures here. I will take you. This is the STL file, right? Only the lines are representing. And what is our objective? To take a plane. This plane, you see, this plane, where you have taken this plane at 34 height. You can see here the value I have and 34, right? At 34, it is calculating all these cross sections, right? And in these cross sections, when one triangle we take, everywhere we put the concept of tail and head, right? So T7 and H7, right? So S7 the head and this is the tail. Okay, so in this way, these triangles we got the intersection point, and what we are going to receive is a line. And now the next question comes, how to connect these lines? They are not in sequence. Your program can read first this, then this, and then it can move to on this side, then take this can be the second, right? So what is required? We have to connect them in a logical sequence, right? P1, P2, P3, and then we have to number them, P1, P2, P3. This information we are going to write in a CLI file, right? I have told what is anybody know about the CLI file? Please write yes or no. CLI file or SLI? So I will take it to the, I come to know that STL file is known to you very well. Very nice. Very good course going on. So I will take to the SLI file. Yeah, any reply? And in between, if you want to ask anything in this programming, how we have developed the logic or how we have connect these points, you see here on the database itself, the segment 1, 2, 3, this is the way we receive the segment, right? Tail and head. Okay. And this is now we have rearranged them, the new segment. This is the old segment connected to the fourth point, then the third segment, sixth segment, fifth segment, and this is the new segment. So now you see, this is connected to 50 50 34. Now 50 50 34 is connected to 34 50. This 34 50 is now connected to 0 50. This 0 50 is now connected to 0 34. Okay, so I'm coming back to the PPT again, right? This is the way we are exporting the STL file from the different softwares, right? Let me take you to the next. So this is again with center is different. Here I have taken the center as the cube center at origin. So everywhere, because the unit size is 10, so everywhere we got the 10, 5, 5, 5, and here we cube is centered at the origin 0. So everywhere it is, we receive this. Okay, now coming to the STL file. I hope you have gone through very well to the STL file. Say yes or no, so I can skip the STL file introduction and various consistency rules, and then we will jump to again to the programming part, how to generate the nozzle path again. How to manipulate STL file, okay. So this you know, or this is your question? Since we gone through the STL file, one triangle, right? You see there are some consistency rules we can recheck, like the number of faces must be even, okay? And the number of edges must be a multiple of 3. Then 2 times the number of edges must equal 3 times the number of faces, right? So based on this, because the requirement of an STL file, it should be a closed volume. There should not be no hole, no puncture. I am coming to that, okay? So this is the STL file you got. Let me take you quickly through the STL file, right? This is how you vary the number of triangles. The same geometry, both geometry are same, but it is lost the designer's intent. become the planar section, and here number of triangles are very high, and you can see how the number of triangles are varying. Okay, now you see how you export the parameters. So two things you control, the chordal and the angle control, right? So based on this, you decide how many triangles are generated. Exact number you cannot control, but point is this, depending on the file size. File size will keep on increasing. The memory size requirement will keep on increasing. The computational complexity will keep on increasing. Okay, so this is how the STL file variation can be done in the different geometry by the different parameters. This screen I have shown you the SolidWorks, right? Those who have already done with the SolidWorks, they can check how to export the STL file, okay, and control these parameters. Now coming to the bad STL, right? What happens when you work with these small printers? Everything seems very fine. You can have a geometric model, you can give to the Cura or GIS slicer, and you can generate. But many a times when you try to print a typical part, lot of errors are coming. The errors like that, whatever we have, our nozzle, our STL file has to be in this way. This is the normal, right? And these fingers will show you the way the vertices are written in a counterclockwise manner, right? So like this, counterclockwise, it will be there. If this rule is not followed, you will not be able to identify whether the contour is internal or whether the external contour. And I hope you know the importance of identifying internal and external contour. Say yes or no, external and internal. Any model, any part will be solidified between the external to internal. But if you reverse this, your machine will print something else. And if you do this mistake on every layer, you can get something else. Your part will not be printed, right? So see here, this kind of defect will be there. Like this, here the triangles are missing, right? So these triangles are not available. This has become a hole, right? And these problems are mainly divided into 4 parts. First problem we will discuss today only, the gap, the crack, the hole, the puncture are basically known as the missing facet. Missing facet means what? Let me show you the missing facet first. Let me take you to the missing facet one. Okay, let me open a new file. See this file, STL crack repair. Let me open and run first, then I will come how we are doing this. One missing facet, right? What is the meaning of the missing facet? Be clear. Look at this here. See, earlier I have shown you the triangle, right? Sorry, cube. The everywhere you got the 12 faces, right? You answered very well, 12 faces. Now, how many facets are in this cube? Did you find that one facet is missing? Anyone? So how many faces are in this cube? Can you see here the front? I am rolling it. You find it, one triangle is missing. Can any logic you can propose, you can tell, so you can count that one triangle is missing? You remember I have shown you the program where we have read the STL file of the cube and it is showing you the file. Right? You remember we have read one STL file and it's showing you that how many triangles are there, right? You have already seen on the screen that there were 12 triangles it is showing. So if you know this is a cube, right? So you can count it manually that there should be 12 triangle. But if you take any other file, you don't know how many triangles should be there, right? So number is not known. Your software, your program has to go and check there should not be any hole or anything missing, right? So in this way, we proceed like for gaps and puncture, right? So see what happens, how these missing facets or gaps can come. Look at this. This is the top surface, surface 1. And here it is the vertical surface. So here what happens, very small holes is there, or very small triangle need to be created. Have you heard about the Delaunay triangulation, or how this triangulation is done, whether it is a finite element analysis or any other way, right? There are a lot of algorithms are available how to do this triangulation. One is the Delaunay triangulation, or the Voronoi diagram we use here. Right? So if you put here, I have shown you one SolidWorks screen where you are giving some parameter or some tolerances based on this triangle. Suppose you have given the large tolerances. So what will happen? Your software will not generate the triangle here, but it will leave it as it is. What happens? Because of that leave it is, there will be a hole. Like on this screen, you can see here, this is the top surface and this is the other side surfaces. What happens? Because this is less than your tolerance. Suppose your tolerance say 2 millimeter, for example, and this is 1.5 millimeter. So what will happen? Your software like AutoCAD or Fusion 360 or whatever you use, it will not generate the triangle. And if it is not generated triangle, what may be the harm to that? Anybody would like to reply? If suppose there is no triangle to that, what is the harm? Such things may lead so many, the part will not print properly, okay? So you see, the lot of errors will come. I'm not jumping into all such errors. Let me focus only to the missing facet problem. See, what is there? There are two things. One is the valid model and another is invalid model. What is the valid model? Valid model means no holes, no puncture, no degenerate face, no overlapping, nothing. So like say this is the model you have generated from Pro-E or CATIA. The next step you need to do such kind of slicing, right? Third step, within this slicing you need to generate this kind of toolpath or the G code, whatever you said earlier, the G code, right? Now suppose second case, here two triangles are missing. Okay, if these triangles are missing, what is going to happen? You will have this information. This is generated, and what happens? Once you generate it, look at the top view, because there is no triangle, so here no edge is generated. Right? You see over here, edge will not. Now what happens if you generate the G code from this contour information? There is no edge where the nozzle will go back. So nozzle will move for the infinite length. And that is the error generated. That is why you said the part will not print properly, because now your system will hang up, or I don't know what kind of error it will show you on the different software platform, but this will not take it to the successful part printing, right? So here we have to convert any invalid model into a valid model, right? Now there is another algorithm to get this. Say for example, I think that I have up to 6:30, right? I have time up to 6:30, okay? So see, such kind of
Yes,
gap
sir.
will be.
Yeah.
Yes, sir.
Okay.
No problem,
Okay.
sir. 5-10 minutes or 10 minutes or nothing problem.
So, okay.
So
I
after
will
that,
conclude by 6:30.
yeah,
No
there is
problem.
a test actually. So test is that we will given the link and then they will solve it later on like that. So
Okay. Since it is the last session, I will try to finish it. See, this is the gap. Now you remember what we have done. I have started with a cube, right? So you remember, if this cube I will take over here, okay, so this will be a triangle, right? Now suppose I numbered like 1, 2, 3, 4. Okay, so what is going to happen? This everybody knows about the STL file. Everybody knows it is showing the normal, right? And it is showing the edges, right? So what will happen? This will be written like this one, and this will be in a counterclockwise. Remember, right? So the edge will be 1, 2. Next edge will be 2, 3, and next edge will be 3, 1. Is it okay for everyone? Please keep on replying. Okay, now look at this. What happens if I take this also as a counterclockwise? What the edges I am going to receive for this triangle B, and this is triangle A. So this is for A, and now let me know what I am going to receive for B. Okay, for B I will going to receive this way: 1, 3, okay, 3, 4, and 4, 1. Okay, now you notice the pattern. This is the common edge. What happens? Within A we have received 3, 1. Okay, and in the B we have received 1, 3. Right? So this is the common edge, but written in a different way. Here it is 3, 1, and now in this triangle it is written as 1, 3. Means what is, if it is a valid solid, we assume all facets are available. Nothing is deleted. So if we check for all 12 facets, we can store in another separate file. Every edge will have its counter colleague. Suppose this 1, 2 is there, this 1, 2. So from the bottom there will be another edge and you will receive 2, 1. Right? Is that clear? Every edge in a STL file, if it is a valid means complete, no puncture, no hole. Right? This will be have a counter. Now what happens? Suppose this B triangle has to be deleted. Now we delete this B triangle from the STL file. What will happen? 3, 1 will be there, but this 1, 3 will not be available. Got it? So the moment you will not receive this 1, 3, you know there is something missing, something is wrong, or some triangle is not available, and it will lead to an invalid solid. You will not be able to generate the contour information, and hence the G code will not be a foolproof. See what happens here in this figure I am showing. This is the gap. This is facet B. So you will receive 5, 2. But because this side gap, so 2, 5 will be missing. Right? So we need to identify this gap. In this way, we will be identifying what are the missing facets. I'm not going into the detail algorithm at the moment, right? We can discuss later at some other time how to do this in the programming. Okay, I will show you the MATLAB program. So this contour we inform, right? Now once we know this is the gap, okay, so this gap has to fill. How to fill this gap? You have already opened the STL file in the notepad. That is the ASCII format. Binary we cannot read. ASCII format file is human readable. We can read it. Even you can write STL file, right? Just by typing it without making any jump, without going to SolidWorks or CATIA or anywhere, right? So this gets filled by the triangles like this. Okay, which triangle is better, that will be decided by the some algorithm again. Okay, this gap filling process has to also follow where the normal will be there, and it has to be in a counterclockwise, right? The same has to go into the counterclockwise every triangle, right? So you see here the first triangle you can fill like this, the second triangle, right? This third triangle. Okay, I'm not going. If you have any question, you can ask. Then I will jump into the detail how to fill this gap. And still, you see everywhere it has to be counterclockwise. You see here the way it is the counterclockwise, and normal pointing towards the outer side of the body. outer side of the geometric model. If suppose normal is inverted inside, then your nozzle will again, or your machine will again get confused which part has to be solidified or where to deposit the material. Okay. So even in this external contour and internal contour, let's say for example, in a computational method, this will be defined as a counterclockwise. So you know this is the external contour. Now inside contour will be defined like in the clockwise in this way. So based on this direction only you are deciding which is. Now suppose it is revert, right? Right now in this position your machine will generate the G code like this. But suppose this direction is reverse. So this contour will become redundant and your machine will print the part inside this. Got it? So these kind of issues are there with the contour information and contour writing. So first you have filled this gap. Now your STL file will become foolproof, right? Now look at this here. How many facets are missing in this? Anyone on the screen? How many facets are missing? Can you identify? 2. Thank you. Like this, now we have filled. But you see here, it is not a queue because there is no way to get the designer intent. But here you see they are the normals are intersecting with each other, pointing towards, right? So this contour is not, this means clockwise or counterclockwise is something wrong. Now see in this case, see this edge, this is coming like this, right? And here this edge is coming like this. So this face is just like you, right? Let me show you to the MATLAB program. Let us run the STL crack repair file. Okay. So first we'll complete this. This time I will open you the same file with two facets, right? Missing STL2 missing facets. Okay. This is just some sample files I have created for quick discussion writing. So you can see this STL file, right? The same STL file I have shown you how it look like if you open it in the notepad, right? So you see the two facets are missing. Okay. Now see here, the program is asking press 0 to fill the hole. So let me put the 0. Something error. Oh, sorry. I think instead of 0, I press the O. Okay. Now press 1 to correct the orientation, 2 to generate the text file respectively. We can have a new text file. Sorry. ये दूसरी screen पे आ गया है. Yes. See here, the file is filled, the gap is filled, but the orientation is not correct. You can see here, right? Now let me say to correct the orientation, 1 to correct the orientation. So 1 to correct the orientation. Now see the orientation is okay. So this program will tell you, you can write this file back to the same STL file, right? So because now you know how the STL file is written, you can type it. So you can ask your program to type 2 more triangles in the same STL file and save it again. So let me put it GHRCE. Okay, the new file name sorry, first let me give 2. Asking for the new file name GHRCE. You can see in the right the current, I hope you know the MATLAB. So you see in the current folder there is no GHRCE file. Okay, let me put this file. The new file is generated GHR, this one, right? Let us open this file in the editor. Now you see here, solid corrected file by PK Jain, the facet normal like this. You see here, now this file contained the complete 12 triangles. Earlier there were only 10 triangles, 2 were missing. So this you have to do in the program by your own. So you see this program is written. If you want anything where what we have done, I will be happy to share that which line representing what. Okay. So this is the STL repair. Now since we have done this repair, okay, file is generated. Now we can move to the generate the nozzle path. We will move to the slicing first, right? So this is the cube file. Let me go back to the slicing, right? Repairing done. Now we are going for slicing. Let us run the slice. The entire additive manufacturing cycle I am trying to show you, okay? Slicing contour, okay? Let me take again a cube. Last I have shown you on the 34. Let me take a 25, okay? So this is the STL file in 25. This is the contour information you got, and this is the contour information, P1, P2, P3, right? If you have any question, you can please keep on typing here, okay? So you see, this is the contour information you got at 25, right? You know, you can put the for loop and get the successor information, right? I'm not going into that moment at this moment, okay? So you see this information. Now this information is written into the file. So these intersection points are written. Let me also check where. We have written this in the XLS, right? Data.xls, data.xls. Let me open it outside MATLAB. So you can see this is the Excel file, and you see this information. These points are written in this Excel, right? Now we developed another program to generate the G code. Okay, this G code M code text. Let me delete this G code M text code. I have deleted. This is the nozzle path file. Let us run this nozzle path file. Okay. So this is the nozzle path file. This will go and read this file. XLS read. We have written the data from the slicing program just to keep the size in our control, right? In the data.h. Now it will go and open the data XLS file. Okay. And once it is open, and it will read and generate the nozzle path. Okay. Let me go back and close all of them. Okay. So let us run this nozzle path. Okay, now look at this in the bottom side. It is asking input size. Okay, let me give 5. The temperature at which bed needed to be heated initially, let me say 200. Temperature at which nozzle needed to be heated initially, let me say 180. And you see over here, the nozzle path it is generated. Got it? We have taken the step sizes 5. Okay. So this is the nozzle path generated. If you want to see it again, let me run it again. Okay. Run. It is again asking for input size. This time instead of 5, let me put 2. The temperature 200, 180. See, it is generating the nozzle path. You can see on the screen itself. Right now, this nozzle path is generated, and this information is not stopped here. Right, what we have done, this information has to be written in a form of G code and M code. Right, so you see here this file I have deleted. Right, now let me open it again. New file is generated. Now those who have talked initially, the information you have generated and supplied to the machine in a form of G code, you can see here G code M code for 3D printer nozzle path. M40, this is the temperature we have given, 200, 180, G28, G, everything. The whatever the information you have generated in a form of coordinates, now this everything is written into this form. This file directly you can give to your 3D printer. You don't need any slicer, any KISS slicer, or any Cura or Magix or anything, right? This is the way you reached to this. Right, so this is how we have done the slicing. Okay, this is the way how you take to the slicing. This is the exploded view, you can say, right? And we have generated this information, all this line information, and connected them in the logical sequence, right? So to start this in the programming, what we have done, we have taken just a triangle and a plane, and we got these 2 points, right? This is another view of those 2 points, another view of those 2 points, front views, you can say, right? Now, see, they converted this information into a mathematical model. So everywhere you have this line equation, right? And 1 line, 2 line, 3 line, and this is the plane. So you are getting the intersection at this point and this point. Got it? So this parametric equation of line to be developed, this is taken into geometry into the matrix form for the MATLAB. Then you can calculate, find out these intersection point, and you see here, these are the intersection point in top view we have got. Right? So this is for one triangle. Now in your STL file, you have thousands of triangles. Once you can do this exercise for one triangle, you can take it up to the thousands of triangles, no issues. Okay, so in your program, you can run in a for loop, right? You have to take care of such cases. See the first cases, triangle can completely lie on the plane itself. Another case, line BC line on the plane itself. Another case, this one vertex lie on the plane itself. So what will happen? It will give you 3 point, 1 point intersection, and these 2 point also will become intersection, so total 3 point. Then you need to filter this information, and this can be happen for any triangle, right? The next case like this. Now, this is the arrangement of the control logical point. The first point, you see the Z25 I have shown you, right? So you see here what happens. The first point is 0, 25. Okay, this is connected with 0, 0. Now we will search this head 0, 0 where it is available in the tail. So you see here, this you find here 0, 0, right? This is connected with 25, 0. Now we will search this 25, 0, this one. You got the 25, 0. So this way you connect them and you see they are connected in a logical sequence. So this will lead you, give you the contour in a logical sequence P1, P2, P3, P4 like this. Right? And this will allow you to get this kind of information from P1, P2, P3, and then it will lead to the nozzle path. Right? This information is going to be written in a CLI file for the machine use. Okay, so what is there in the CLI file? All these contour points are there. These points in a form of XY, XY, XY written in a CLI file. You see here, this is the contour, head start, ASCII, unit, layer thickness. Now this is layer at 50. So this is kind of 2.5D. Means you have this information and you know the layer thickness, how much it has to be extruded. Right? So you see one contour, total number of points 5. Then 5x y0, x5 500, y300, x0 y300. Right? This way it will continue. Right? So you see here, you got here the 5 points internal. Here it's only external contour. Here also the internal contour, because you see at this height you will receive the internal contour also. Right? So because of the time constraint, I'm not going to tell you, or this nozzle path I have already shown you. A CLI file, nozzle path, and the typical part will be like this. Right? Now these things you can take for the biomedical application. You remember the X-ray, you remember the CT scan, right? You see here, you can import these things into the MATLAB. Now you have to identify where the blood vessel or bone depend on the Hounsfield value. Okay, so you can see here this kind of model you can print, generate, and you can take up this rendering model, right, for bone printing, right? See, this is the latest one we have done to identify this mandibular bone. This information we can use. This is done in the mimics, the very much needed software included in your course. Even though we have developed the image processing programs, which you can directly take up to the CT scan and MRI images and get the contour information. Remember here, what is required is the contour information. Okay. So like this, you can generate this mandibular, and we have done a lot of CAD operations. So this is the printed with this tumor, right? Then this is the final bone for the doctor's rehearsal purpose. Okay. So like this is another example which Dr. Abhay was talking about, the dentist. You see here, we have identified, the root canal treatment. So mostly depend on the doctor's experience. They use the X-ray technique, and based on X-ray, they identify the direction. So this is what we have developed here, the external contour, internal contour. You remember what the programming we have done and how it is going to be applied. So here we have identified this direction. This is the identified optimum direction where the doctor has to drill within the tooth. So what happens after applying this mathematical information, we find this direction and this information. So you see, this is the direction for the file, tooth file, right? Within this direction, you see here, we have developed a jig 3D printed, which already have a hole in the particular direction. Right, so doctors know they have to put in this whole directory, and this is a lot of validation. The tooth part, the jig part is here, right? Here the extracted tooths are there, so in vitro study is there, right? Like this hole has to be generated over here, right? This is the jig we have created. This is again based on the CBCT scan. So micro scan, we know the geometry of the tooth, we have developed the reverse geometry, and we have put on this teeth, and you see here, this is a different direction, holes are already there. So doctor know that where and which direction they have to put, right? So this is a assisting device or assisting methods, you can say, for the dentist, right? This is the one recent we have done to develop the 3D printed images. So you remember the grayscale and binary images. Okay, so what we have done here, RGB image converted to grayscale image, then image to point cloud conversion. So here what happens, we have given the third dimension. Third dimension to what? Based on the grayscale image. So this image is now become a 3D image, right? This is the fundamental, and you see its result. RGB image, RGB grayscale, image STL file generated. This is the nozzle path, and these are the printed image. Let me see. Yeah. Can you see my hand in my camera?
Yeah, yeah,
Yeah.
yeah.
Right. So this will be the last example I am quoting here, and we will stick to the time, and we can close something for the next session, sometime, right? So this is the picture we have converted from 2D image to 3D image, right? And a lot of things like this we have done for the Jabalpur, the medical college Jabalpur. This is your C4, C5 joints are there, right? So you require a lot of programming techniques as well. You can't rely on open source software, because open source are developed by like us also, right? They are also like our students or somebody who is doing practice and uh, developing open source software and taking it to the U. Okay, these things we will skip. Right now we are working on metal additive manufacturing and aluminium printing. Let me take you one small video of this printing. Okay, let me take this. Can you notice here, just like your fuse deposition modeling, this machine is printing the aluminium. So right now I'm not going into details of it, and we can conclude the session with the hope the future will be in 3D printing, will take you to the organ printing. You are sitting in the Nagpur, already listen to many experts who are working in directly on organ printing, medical field people, right? So with this, we can close this session. I'm thankful to the organizers for this opportunity.
Thank you, Jain
Thank you
sir,
so much, sir.
for a nice session. Dr. Jaju, yes, sir.
Yeah.
Coordinator, yeah. And
Thank
Dean
you so
R&D
much,
of
sir.
our
Yeah, we met Dr. Jaju. We
Yes,
remember
sir.
very well.
Yeah, yeah. Yes, sir. You are helping us all the time. Yes. Even in the earlier FDP also, you have helped us, and you came physically also here.
Yes. Once I visited also, right.
Right,
Yeah.
right.
There are
So we will connect around 7:30. Okay.
Yes, sir. 7:30
Okay.
we will connect, because right now there is a feedback and test.
Fine, sir. I will be joined 7:30. I will keep the system on and everything is connected right now.
Yes.
And just
Yes, sir.
leave for
Right.
lab and come back to my office again at 7:30.
Right. Thank you so much, sir. Thank you so much. Yes.
Okay, thank you. Thank you.